To get an idea of what can happen if we have a large system, where there's more than one wavelength in the system, let's look at a couple of simulations of the simple Swift-Hohenberg model. And so let's start with a simple initial condition, which is just periodic, and it just has the wrong amplitude. And let's simulate what happens. So this is going to be here in the top left window. So let's just run it and see what happens. Okay. So a small amplitude, and it grows to some saturation amplitude, which is not surprising because we know within that space of periodic solutions that pattern is stable. It arises in a supercritical pitchfork bifurcation. You may have noticed that the dynamics here was not really smooth. It was sort of like a little bit jerky. That's not real. That's because whenever it updates the legend here, that takes a little bit longer. And so that's sort of when it always slows down. So it actually is nice and smooth as you would expect. Okay, and so here you see actually the space-time diagram. So initially the amplitudes were small, and then the amplitudes became large and saturated to some periodic pattern. Okay, so now let's see what happens if we perturb this pattern. So we know that if we just perturb the amplitude, it would be stable. That's fine. But now in this large system, we can make that perturbation space dependent, as in we can make a different perturbation at the left side than on the right side. So let's do that. For that, I have to add a perturbation, and I pick some parameters. So and you'll see in a second what the perturbation looks like. So down here, the blue pattern is the pattern we just had, and the red pattern is the pattern that I get after that perturbation. And so now let's just run it and see what happens. Okay, I mean, does all hell break loose, or do we just get some relaxation? Or, well, let's just see what happens. Okay, and you see nothing spectacular happens in this case. The pattern simply relaxes back to the same amplitude as before, even though the amplitude was larger here and was smaller here. And the fact that the amplitude was different in different locations in the system didn't really make much difference here. Note that the perturbation I applied is such that the wavelength, the local wavelength, or at least let's say the distance between the successive maxima, is the same. So it was still, I can't say it was periodic because the amplitudes are changing in space, but there was no change in the local wavelength, so to speak. Okay. So let's now make a different perturbation where we actually squish the pattern at some locations and expand it at another location. So let's see. So here with the amplitude of modulation, okay, so we want to do this. So now you see what I've done is, again, it turns out the amplitude also changes, but that's not the key element. The key element I want you to pay attention to is that this maximum was shifted to here, this was shifted to here. So here the patterns are shifted to the right, whereas here the patterns are shifted to the left. That means here the wavelength is actually larger than here. Here it got compressed and here it got expanded. I just need to change now the parameters a little bit in terms of how long we need to run it. Okay, and then we can just see what happens. Okay, so you see, again, the amplitudes relax again, but things are kind of slow now, actually. Now you don't see much at all, even though here the wavelength is clearly larger than here. So what's going on here? Well, it's just a slow process. But now you see actually the amplitudes become more equal. And with this speed, it's hard to tell whether these wavelengths actually change or not. So let's wait until it's done. And then we should be able to see in the space-time diagram whether the wavelengths actually changed or not. Actually, if you look carefully, it has already more equilibrated, right? So we just have to be a little patient. We could have skipped some of the plotting, but we didn't. Okay, here now you see very clearly that initially, let me first zoom in. Initially, we had a pattern that looked like this, where it was, the amplitude was larger here and at some locations it's smaller, but you also see that the wavelength is clearly longer here than here. And as time progresses though, you see that indeed, no, I shouldn't say indeed, because we didn't really know what would happen, but you see that here they were compressed, and so they move away, they move outward, whereas here where they expanded, things are converging there, and so eventually the wavelength looks more homogeneous here than here. But you notice also, and that's important to keep in mind because that will show up later when we actually do analytical work on this, that the evolution of the wavelength, of the wave number, was much slower than what we saw earlier. When we did this amplitude perturbation alone, it relaxed very quickly. That relaxed within like just 2 or 3 time units, where here, after 40 time units, it's not quite relaxed yet. Okay, but we see relaxation. If we make certain perturbations in the wavelength, they relax back and we get a periodic pattern, at least in this case. We'll later see that that's not always the case, and that will be interesting, but let me not go there yet. We'll do other simulations later. The only thing I want to do still is, well, just to illustrate that we know that when we do the linear stability analysis of the homogeneous state, that there are certain wave numbers that destabilize that state and certain don't. And that was determined by the neutral curve, or that determined the neutral curve. The guys inside the neutral curve were growing modes, and the one outside were decaying modes. And so all the wave numbers away from the critical wave number, which in the Swift-Hohenberg model is 1, but okay, so all the wave numbers away from the critical wave number, they're kind of damped according to linear stability, whereas the ones close to the critical wave number are all growing. And so we should be able to see that in the simulation. So let's do a last simulation where we start with initial conditions that are random. But this happens very quickly. So we need to also change the simulation time frame. And we need to change the time step because otherwise we won't see anything really. Okay, and so now if we run it, as I said, I picked random initial conditions and let's see what happens. So you see initially there was this flash of something you couldn't really tell what it was. It was just a very highly wiggly solution. And now it's still not periodic, right? But you see that it became sort of, has a wavelength similar to what we saw in the other pattern. I can run it for longer in a second, but let's just zoom in first again into what we just saw in the space-time diagram. And you see that initially there's very, very large wave numbers. Like here, you see it's wiggling really fast, which you expect if it's a random initial condition. But as time progresses, these wiggles disappear. As you see right now here, they disappear and it becomes much, the pattern becomes more long wave. It's still not very ordered, but we can, let's just run it for longer now. T max, maybe 10 again, but dt that we want to take bigger again, otherwise we'll be here forever. And so if you just continue now with the same state, then we get, see, now it relaxes to something that's looks, well, it's not periodic here, right? Okay, now this goes away, whatever it is. And eventually it's quite regular. And you see that also in the space-time diagram that the wave numbers are equilibrated, right? They're all, the wavelengths are all pretty much the same. And there was one process, well, here you see these two maxima, they kind of merged into a single maximum. And so that will be something we'll think about later. But the upshot now is that we see that after short initial transients where high wave numbers, large wave numbers may be relevant, they die out, and then we actually only have low wave number, I shouldn't say low wave number, wave numbers close to that critical wave number, which in this case is about 6. Actually, it's 2 pi exactly. And see that it really goes to wave number close to that critical wave number, and the pattern becomes periodic as time progresses. And so it would be nice now if we could describe that process in a simpler system, simpler equation than the Swift-Hohenberg model. The Swift-Hohenberg model, I mean, it's a 4th order PDE, which is sort of relatively complicated. Well, relatively, but I should mention that the same processes you would see if you solved much more complicated equations like Navier-Stokes or other reaction diffusion equations. And so it would be important to see whether we can capture processes like the ones we are describing right now, or we saw right now, whether we could capture those in a simpler form and hopefully even in an equation that would be valid for many different systems. And indeed, we'll find that's the case, and that's our task for now.